So section 5.2, inverse functions. Let's start with one-to-one functions. One-to-one functions, two things are true. Every value in the range has a unique value in the domain. And the second thing is that a one-to-one function passes the horizontal line test. So hopefully you recognize that this is the exact opposite of a function. A function, every value in the domain has a unique value in the range, and it passes the vertical line test. Well, if I'm going to be one-to-one, the opposite is true. So if you recall for inverse functions, how do you find an inverse? You switch x and y. So that is how the definition of one-to-one comes in. All right, if x1 and x2 are inputs, and I should add that x1 does not equal x2, then the f of x1 doesn't equal the f of x2. This is by definition a one-to-one function. Two different values for the input gives you two different values for the output. All right, so I'm not going to go through some of the more basic examples. Read the examples, go through them from page 257 to 260. Your book gives some really good examples, and I don't think I need to do like mapping and things like that with you that you can read and do on your own. Most important thing to know when you are going to find an inverse, which is also going to lead to one-to-one, is that you switch x and y to start finding an inverse function, which actually will lead you to determine whether that function is one-to-one, is to switch x and y. All inverse functions, inverses and functions have y equals x symmetry. All inverse functions with their functions have y equals x symmetry, meaning the f of x and the inverse, this is inverse notation. We don't say f negative 1x, it's the inverse. The way that you read this is the inverse function of x. So this is inverse notation. And if you've done it correctly, the inverse of f and the f and its inverse have y equals x symmetry. Have y equals x symmetry. I'm going to do a couple harder examples. I think that, again, you can read through the ones in the book. I think what we need the most practice with is finding inverses of some complex fractions. So let's look at something like the f of x equals x minus 5 over 2x plus 3. And actually, before we find the inverse, let's do some review, asymptotes, intercepts, etc. This has an x-intercept at 5, 0. It has a y-intercept at 0, negative 5/3. It's horizontal asymptote, end behavior, lead coefficients, degrees match, 1x over 2x. Your horizontal asymptote is at y equals 1/2. And lastly, our vertical asymptote is at x equals negative 3/2. Let's find the inverse of this function. And then let's check it with all this information that we just got here. So to find the inverse, we're going to switch x and y. We're going to switch x and y, and then we're going to solve for y. Okay, f of x, same thing as y. So this is going to become x equals y minus 5 over 2y plus 3. Sorry, I'm going to just do this to kind of separate problems here. All right. All right, so I'm going to multiply both sides by 2y plus 3. So I'm going to work horizontally here just so I have more room. This is going to be x times the quantity 2y plus 3 equals y minus 5. Distribute 2xy plus 3x equals y minus 5. If you want to solve for y, you must get the y's all together on the same side of the equation so that you can factor. I'm going to subtract y, and then I'm going to subtract 3x. So this is going to give me 2xy minus y equals negative 3x minus 5. The reason for this is that now I can factor. Now I can factor. So I'm going to pull out the y, and that leaves me with 2x minus 1 equals negative 3x minus 5. Divide, you get y equals negative 3x minus 5 over 2x minus 1. Improper notation. This is not right. It's given to you as f of x. Your answer should be f of x. And inverse notation. I switched x and y. All of this information should switch. The x-intercept should become the y-intercept. The y-intercept should become the x-intercept. The horizontal asymptote should become the vertical, and the vertical should become the horizontal. So let's check. All right, so the vertical asymptote comes from the denominator 1/2. Bam, 1/2. So the vertical asymptote is x equals 1/2. Okay, the horizontal asymptote, degrees match, divide the lead coefficients, you get negative 3/2. So far, so good. Instead of y equals 1/2, x equals 1/2. Instead of x equals negative 3/2, y equals negative 3/2. These are good signs that you've done it correctly. X-intercept comes from the numerator, set it equal to 0, and you get negative 5/3. Y-intercept, divide the constants. And these are indeed opposite of each other. Okay, so that's not good enough. I mean, I would be prepared that I'm going to ask you to, this is a great review, find all the key information, x-intercept, y-intercept, blah, blah. Do the same thing here. So again, this is a good sign that we've done it right. However, you need to know how to check. And if you're going to check the inverse of the function, when you plug the function into the inverse, that must equal when you plug the inverse into the function, function into inverse, inverse into function, and this must equal x. Okay, so we're going to check. Okay, which way should you go? Should you plug the inverse into the function into the inverse? Which way do you have to do it? It really makes no difference. And then the next question is, do I have to do it both ways? And the answer is no. But don't skimp on showing your work, because it's very easy to say, oh, yeah, it equals x, and put a check mark and be done. I'm going to plug the inverse into the function because that's what I feel like doing right now. So this is going to become the f of my inverse, which is negative 3x minus 5 over 2x minus 1. Okay, and here are your complex fractions. Here we go. X comes out, negative 3x minus 5 over 2x minus 1 goes in, and then minus 5. And I'm going to write it as 5 over 1 just because I think it's helpful. 2x, which is now negative 3x minus 5 over 2x minus 1 plus 3. Okay, then the next step, you need to find a common denominator. Don't you even think about reducing that. That is such voodoo math. Common denominator is 2x minus 1. So I'm going to multiply numerator and denominator by 2x minus 1. And I will use a different pen. Okay, 2x minus 1's with this first fraction. 2x minus 1 times negative 3x minus 5 over 2x minus 1. They reduce out, and you get negative 3x minus 5. Minus 5, when you distribute, nothing reduces. Get 2x minus 1. Once you get past the complex fraction part, I think you're good. Okay, distribute. I have 2x minus 1's reduce, and you're left with negative 3x minus 5 plus 3. When you distribute, 2x minus 1. Do not skip too many steps. You cannot skip from here to the very next step without showing something in between. So this becomes negative 3x minus 5. I, of course, am going to show every single step. Distribute, you get minus 10x plus 5. I like this, negative 5 plus 5. That makes me feel good. Negative 6x. What's that? Minus 10 plus 6x. I like that. Negative 6x plus 6x minus 3. This gives me negative 13x over negative 13, which is x. Cha-ching. Let's take a look at one more. Say that the f of x is equal to x squared plus 3 over 3x squared. Horizontal is at 1/3. There are no x-intercepts. Vertical is at x equals 0. It's a bouncer. So let's find the inverse. So this is going to be x equals y squared plus 3 over 3y squared. Multiply both sides by 3y squared. So you get 3y squared, 3xy squared. You get 3xy squared equals y squared plus 3. You want all the y's on one side so that you can factor. So this becomes 3x y squared minus y squared equals 3. Factor, you get y squared, 3x minus 1 equals 3. Y squared, equals 3 over 3x minus 1. Root both sides, and you get y equals the square root of 3 over 3x minus 1. Let's check our notation. No plus or minus. If you do a plus or minus, it's going to fail the horizontal line test. Okay. That's not true. The function may or may not, the function passes the vertical line test, which means the inverse passes the horizontal line test. But this function right here will fail the vertical line test. We'll plug it into our calculator and see what we get. That might be easier to see. Let's do a quick check. I think it's easier to plug the inverse into the function. I don't know why, that's just what's sticking out for me. So I'm going to plug the function inverse into the function. So x, which is now, let me write this down. I'm going to plug the inverse into the function. So this is going to be the f of this big thing right here. So x, which is now the square root of 3 over 3x minus 1. You don't have to rationalize this. You don't have to rationalize this. It's kind of a pain, and it's not the purpose of the problem. I'm not trying to test, do you know how to rationalize? Over 3x, 3 over 3x minus 1 squared. No reducing that out. Squared, okay, great. Root sign goes away. So you get 3 over 3x minus 1 plus 3 over 3 times 3 over 3x minus 1. Because my denominator is a monomial, I might just multiply by the reciprocal. We'll see. This is 9. Actually, I'm going to just multiply by 3x minus 1. If you want to multiply by the reciprocal, go ahead. I'm not a huge fan of that. I'm going to multiply by 3x minus 1 over 3x minus 1. I didn't plan ahead very well, so I'm going to run out of room on my paper. Shoot. So 3 over 3x minus 1 times 3x minus 1. The 3x minus 1s reduce out, and you get 3 plus 3, 3x minus 1 over 3x minus 1s reduce out, and you're left with 3 times 3, this 3 out here, and then the numerator, which is 9. 3 plus 9x minus 3 over 9. 3 minus 3 is 0. 9x over 9 is x. Got to know your complex fractions. So we did indeed find the inverse correctly.